Hello everyone, welcome to the lecture again. Today we are going to study impact, particularly the direct central impact. So let me define what is impact. Impact is basically the collision. So it is the collision between two bodies that occurs in a very small interval. Okay. And to study the impact, we have to define what is the line of impact. So let us say I have a body, let us say A, which is moving in this direction with a velocity V A. I have another body, let us say B, which is moving in this direction with velocity V B. Then the common normal to the surfaces in contact during the impact is called the line of impact. Okay. So, let us look at the common normal. So, here this is the common tangent and this one is the common normal. So, therefore, this is the line of impact and this is the tangent to the contacting surface. Let us look at what is direct central impact. If the velocities of the two particles are directed along the line of impact, then the impact is direct impact. For instance, let us say I have a particle A which is moving with velocity V A and I have a particle B which is moving with velocity V B and they are moving along the line of the impact. So, along this line, and of course, for the impact V A has to be larger than V B, then this is the direct central impact. Over here also it was the example of the direct central impact. Now, let us look at the oblique central impact. So, here or it occurs when the direction of motion of one particle or both particle is at an angle to the line of impact. For example, let us say I have a particle A which is moving with velocity V A like that and I have a particle B which is moving with velocity V B like this then the common tangent will be this and the line of impact will be that. So, this is your line of impact and this one is the tangent to the contacting surface. Okay. So, you can see here that the direction of motion of the particles are at angle to the line of impact, therefore, this is oblique central impact. Now, let us analyze the direct central impact first. So, we are going to analyze the direct central impact. So, let us say again as we are keep saying we have a particle of mass m a, let us say this is a, it is moving with velocity v a along the line of impact, and we have another particle b, its mass is m b and it is moving with velocity v b. And of course, for the impact v a should be larger than v b. This is the case before the impact. Okay. And after that we have impact. So, this was particle A and that was particle B. During the impact both of them travel with some velocity, let us say that velocity is v naught, and during this time because this is the impact there will be impulse. So, first there is a deformation impulse. So, the body will deform and then there will be restoration impulse. Okay. Let us say the overall time for the deformation impulse and for the restoration impulse is t. So, from 0 to t naught time there is deformation and then from t naught to t time there is restoration. So, this is the case when the impact happens. So, this is during impact, and then after the impact we have particle A and particle B, they travels with a velocity v a prime and v b prime. This is the case after the impact, and we want to find out what is the velocity after the impact, that means what is v a prime and what is v b prime. So, since there are two unknown, we need two equations to solve this problem completely. As I said, let us say total time of contact or impact is t, and during this time the velocity of A and B is v naught, and the deformation time is t naught and the restitution time is from t naught to t. So, let us use the impulse momentum relation. So, this is something that we can use to find out what is the momentum after the impact. So, impulse momentum relation, it tells that if the initial momentum is p1 and the impact is f dt, then the final moment will be p2, or I can find out what is the impact integral f dt, that is p2 minus p1. Now, let me define the coefficient of restitution. It is denoted by E, and this is the ratio of the restitution impulse divided by the deformation impulse. So, we have a restitution impulse divided by the deformation impulse. Let us look at the deformation impulse. So, the deformation is from 0 to T naught. So, 0 to T naught. Let us say the deformation force is F d. So, it is F d dt, and the restitution is from T naught to T F r dt. Here F d is the contact force during deformation, and F r is the contact force during restoration. Okay. Now, let us use the definition of E, let us call it equation number 1 for particle A. So, for particle A, E will be, let us first look at this term 0 to T naught F d dt. F d dt will be P2 minus P1. So, P2 will be the momentum after the deformation. Okay. So, P2 will be MA VO minus the P1, which is the initial momentum. So, MA VA, and Fr dt will be again P2 minus P1, wherein P2 will be the momentum after the restoration has happened. So, that is MA VA prime minus the P1, which is the initial momentum before the restoration. So, it is MA VO. From here MA will get cancelled and we get E equal to VA prime minus VO over VO minus VA. Let us call it equation number A. Now, let us use the same definition for particle B. So, for particle B, we have E equal to 0 to T naught F d dt. So, F d dt will be P2 minus P1, and P2 is the momentum after the deformation. So, that is MB V naught minus the initial momentum MB, it was travelling with velocity VB, and here I have Fr dt. So, Fr dt will be again P2 minus P1, and P2 is the momentum after the restoration has happened. So, that is MB VB prime minus MB V naught. So, again the MB will get cancelled and we have E equal to VB prime minus VO over VO minus VB. Let us call it equation number B, and remember our equation number A was E equal to VA prime minus VO over VO minus VA. This was our equation number A. Now, here the unknown is VO, because that is something that we do not have access to, therefore, we have to eliminate VO, and we can eliminate VO from equation number A and B if we use the identity that if suppose you have a quantity A which is B1 over B2 and the same quantity A is equal to let us say C1 over C2, then I can write down A as B1 plus C1 over B2 plus C2, or I can write down B1 minus C1 over B2 minus C2. Okay. This we can prove very easy. So, let me just prove this. So, from here, because A is equal to B1 over B2 and the same A is equal to C1 over C2, therefore, B1 over B2 equal to C1 over C2, or I can write down B1 C2 equal to C1 B2. Now, let us start with A. A was C1 over C2, we can multiply it by B2 plus C2. So, C1 B2 plus C2 divide by C2 B2 plus C2, and this I can write as C1 B2 plus C1 C2 divide by C2 B2 plus C2, or B1 C2 plus C1 C2. Herein I have used C1 B2 equal to B1 C2. So, this divide by C2 B2 plus C2. Now, C2 will get cancelled and you will have A equal to B1 plus C1 divided by B2 plus C2. So, therefore, let us use this identity and therefore, E can be written as, because E is this and E is that, therefore, E will be VA prime minus VO minus VB prime minus VO over VO minus VA minus VO minus VB, and this VO will get cancelled with that and this VO will get cancelled with this. So, we get rid of VO, we get E is equal to VB prime minus VA prime over VA minus VB. Okay. And note that what was VB prime and VA prime? Well, the difference gives you the relative velocity of the separation. So, this is the relative velocity of separation, and the bottom you have relative velocity of the approach. So, this is the velocity with which the particles are coming to each other, and VB prime minus VA prime is the velocity of the separation. Let us call it equation number 1. Now, we need one more equation, and for that we can use the fact that the contact forces are equal and opposite during the impact. Therefore, the linear momentum of the system, so here system means the system of two particles, will be conserved. So, therefore, we have MA VA plus MB VB equal to MA VA prime plus MB VB prime. Let us call it equation number 2. Now, we have two equations and two unknown, therefore, the problem can be solved mathematically. Let us look at some of the examples based on this concept. So, this is the first problem statement. A 20 million gram railroad car moving at a speed of 0.5 meter per second to the right collides with 35 million gram car at rest. After the collision, the 35 million gram car moves to the right at a speed of 0.3 meter per second. Determine the coefficient of restitution between the two cars. Okay. Now, in this question it is given that the railroad car has a mass of 20 million gram, let us call it A, and it is moving with 0.5 meter per second to the right. Car B, its weight is 35 million gram, it is at rest, and after the collision, let us say car A moves to the right with a velocity of V A prime, and it is given that car B moves to the right with a velocity of 0.3 meter per second. Let us take this as positive x direction. To find out V A prime, we can use the conservation of momentum. Of the whole system. So, we have M A V A plus M B V B, this is the momentum before the collision, equal to M A V A prime plus M B V B prime. So, M A and V A is given 20 into 0.5 plus V B is 0 equal to M A V A prime plus M B into V B prime, and this gives you V A prime equal to minus 0.025 meter per second. Therefore, we have to change the direction of the V A prime. Now, we can find out the coefficient of restitution E, which is equal to the relative velocity after impact divided by the relative velocity before impact, or we can write down V B prime minus V A prime over V A minus V B. So, this comes to be 0.3 minus 0.025 divided by 0.5 plus 0, which comes out to be 0.65. Now, let us look at another problem statement. Question number 2. Two cylinders move along a road in a frictionless manner. Cylinder A has a mass of 10 kg and moves to the right at a speed of 3 meter per second, while B has a mass of 5 kg and moves to the left at a speed of 2.5 meter per second. What is the speed of cylinder B after impact for a coefficient of restitution E equal to 0.8? And it is also asked to find out what is the loss in kinetic energy. So, here it is given that you have a cylinder of mass 10 kg, let us call it A, it is moving with 3 meter per second to the right, collides with 5 kg cylinder, let us call it B, which is moving at a velocity of 2.5 meter per second to the left, and after the collision, let us say cylinder A moves in this direction and B moves also in the positive direction. Okay. And in the question statement, we have been asked to find out what is the speed of B and the energy loss, okay, the kinetic energy loss. So, we can use the conservation of momentum for the whole system, m a v a plus m b v b equal to m a v a prime plus m b v b prime. So, m a is 10 into 3 minus 5 into 2.5 equal to 10 v a prime plus 5 v b prime. We can rewrite this as 17.5 equal to 10 v a prime plus 5 v b prime. Let us call it equation number 1, and now use the definition of coefficient of restitution E, which is the relative velocity after impact divided by the relative velocity before impact. So, this is v b prime minus v a prime over 3 minus 2.5. So, E is given, it is 0.8. So, therefore, 0.8 into 5.5 equal to v b prime minus v a prime, or we can write down 44 equal to minus 10 v a prime plus 10 v b prime. I have just multiplied both side by 10. Now, we can add 1 and 2. So, we get 61.5 equal to 15 v b prime. This gives v b prime equal to 4.1 meter per second. And if we put this in equation number 2, then we get v a prime, which is 0.3 meter per second. Let us now look at the change in kinetic energy. So, kinetic energy is half mv square, therefore, the change will be half m1 v1 square plus half m2 v2 square minus half m1 v1 prime square minus half m2 v2 prime square. Okay. Let us put the values. So, we have half into 10 into 3 square plus half into 5 into 2.5 square minus half into 10 into 0.3 square minus half into 5 into 4.1 square, and this gives you 18.15 Newton meter. So, this is the change in kinetic energy. With this, let me stop here. See you in the next class. Thank you.